Okay, so sometimes when we have a function, not always, but a lot of times when we have a function, we can also talk about what's known as its inverse function. And let's just use f. Maybe we can do it for any function we want, but letter anyway. For function f, the inverse function is denoted, if it has an inverse, if it looks like -1 power, but for functions, the -1 power means the inverse function, not -1 power. Because -1 power means something totally different if you're just talking about a number. This is an inverse function. So the inverse function is, first of all, denoted by f to the -1 power. And just like the name suggests there, guess what the inverse function does? The inverse function, well, it's going to undo what the f function did. It inverts it, right? Quote unquote. That's what an inverse function does. It undoes what f does. I don't know if undoes is a really word, but it will undo what f does. For example, let me give you an example. All right, here's f of x. F of x is 2x. Turns out f inverse of x, if f is 2x, f inverse of x is x over 2. If you think about it, you might think about that, come up with that, but we'll do more complicated ones. But this just makes the point. A couple of points, matter of fact. Let's do a table of values here. 1, 2, 3 for x. So if f of x is 2x, then my y value, what have I got for y values? 2 times 1, 2 times 2, 2 times 3. So 2, 4, 6. So by this very informal definition, what happens over here, let's look at this. So this is what f does, right? It takes 1 to 2, 2 to 4, and 3 to 6. So f inverse should undo those. So it should take these and undo those. In other words, go back to what we started with. So what does x's 2, 4, and 6 do over here? Well, now change the function. So now y is this. So what is y when x is 2? Well, it's 2 over 2 is 1. When x is 4, y is 4 over 2, that's 2. And when x is 6, y is 3. See that? That's what it does, okay? It takes the x's, maps them to y, but then the inverse takes those as x's and maps them back to what you started with. All right. So, one thing to note about this, what can you tell me about these tables? If that's not obvious there. They're flipped, aren't they? The x's over here are the y's over here, and the y's over here are the x's over here. The tables have flipped. That's what inverses do, and we'll do a problem like that. So note that. So the tables are flipped for inverse functions. Call it f and f inverse. The tables are flipped. The x's are the y's are the x's for your inverse function. Now, it also goes vice versa. This is another point here. All right, so let's start with my inverse function here. All right. So this one, we started with this table and went to this table. Let's start with this table. We'll just do one. Let's start with x is 8. the y is 4, sorry, 8 divided by 2 is 4. Well, take a look at this. It works both ways, doesn't it? So now, if I take the y here as my x, what happens? It flips again, okay? So that's a point too. You know, if we go the other way, it works the same way. It flips those around, okay? It flips it whichever way you go. Now, the reason I point that out is the first thing we're going to do with this, or I'm going to show us anyway, is a way to note this, what inverse functions do, is with the composition. So essentially, if I start with the F inverse, if I start with the F inverse here, now let's do this. If I start with the f of x, 1 goes to 2, well then what f inverse does is it picks up at 2 and goes back to 1. So if I start at 1, I wind up at 1. So the way we can note that is this. If I do the composition, f inverse of f of x, in other words, I start with x, do the f of x, and then take the f of x, plug it back in the y, plug it back in, I wind up with x. Right? If I start with x, 1, following example. If I start with 1, f of x, that goes to f of x, which is 2. And then f inverse picks it up, 2, and goes back to 1. I wind up back with x, you see. And it works the other way too, that's why I showed you this. If I start with f inverse x, and plug that into f inverse, 4, and then plug that into f of x, 4, I get back to 8. So either way you go, if you do that process for the inverse, you wind up back with x. Okay? Sort of see that? Well, that's what we first do, is verify a function in its inverse. So this is the way that's said. Verify the functions are inverses. It's f of x equals 4x minus 3, and g of x equals x plus 3 over 4. Here's what they want you to do on that. They want you to do this for both of those. Both of those for this. So what this is saying is, and they didn't note it, but g of x is the inverse, in other words. This is my inverse of this f. That's the way you take it, okay? So what they want you to show is this is x and that is x. So in other words, do the composition this way and then do it the other way. So g f of x, see what that equals, and then do f g of x. That's what they want you to do. In this problem, they want you to do the composition both ways. Now, if they are inverses, what should we get as the answer? Should get x. So they just want you to verify that. All right, so what's g of f of x? So this is just like we were doing a second ago. All right, g of f of x, so do the f first, so g of 4x minus 3. So plug that in to the g function right here for x. So that's 4x minus 3 plus 3 divided by 4, right? Plugging in 4x minus 3. 4x plus 3 minus 3. How about that? 3's cancel, you got 4x over 4. Sure enough, get x. And it works the other way too. F of g of x, so that'd be f of g of x. So you replace the g of x by x plus 3 over 4. See what that gets you. Well, now we're plugging in to the f function, x plus 3 over 4. So it'd be 4 times that, 4 times the x plus 3 over 4, minus 3. And sure enough, 4's cancel, so you have x plus 3 minus 3. That winds up being x. So that's what they want you to do on those. Now, I said not all functions have inverses. Because here's the restriction on it. For f to have an inverse, f inverse. Sometimes talking and writing at the same time doesn't work. All right. For f to have an inverse function f inverse, f has to be what we call 1-to-1. So you have to have a function that's 1-to-1. And I may have mentioned it before. And the one way we're going to check it, the way I have us do it anyway, check it for 1-to-oneness is using the horizontal line test. To be a function, it has to pass the vertical line test. To be a 1-to-1 function, it has to pass both of those. Horizontal, to be 1-to-1, it has to pass the horizontal line test. What that basically means, 1-to-1, 1x for 1y, and 1y for 1x. 1-to-1. 1x, 1y, 1y, 1x. Both ways. But that's horizontal line test. So this question, a couple of these, does f have an inverse function? Let's do it over here. Okay? So the first one I'm going to do, f of x is the square root of x minus 5. I think they may have it already graphed for you, but we know what that graph looks like, right? It's been a while, but that's the square root graph shifted 5 units to the right. So a really quick version of it looks like that. So the question is, does this have an inverse function? Well, that really amounts to, does it pass the horizontal line test? In the horizontal line test, you just think about horizontal lines here, going through it everywhere. So maybe I should have done the other way, but that's all right. But yeah, since that keeps increasing to the right there, yeah, this is going to pass wherever you draw a horizontal line. To pass the horizontal line test, it doesn't cross it more than once. So yes, this does have so it does have an F inverse. Okay? Now let me mention this one. Number 2. Does this one have an F inverse function? F of x equals x squared minus 4. Well, again, with the shifting, x squared minus 4, real quick. X squared shifted down 4. vertex down there at 0, -4. Yes or no? Inverse? No. Okay. No F inverse here. It fails the vertical line test, right? Horizontal line test. HLT. It's still a function. It passes the vertical line test, but it doesn't pass the horizontal line test, right? It intersects it twice. Multiple horizontal lines twice. So that one would not have an F inverse. However, number 3 is this. Note this. Okay, so same function. But x greater than or equal to 0. Restrict the domain there. Does that have an F inverse? If I restrict it here, what does this mean? I only want x greater than 0. So what part of the graph am I wanting here? Just basically the right half of that. So instead of the full, whoops, vertex is 0, 0. 0. Isn't that the graph now? F inverse? Does that one have? Yes, that one does have. So you see, if, because now it passes the horizontal line test. If we have one that doesn't pass the horizontal line test, sometimes we just restrict the domain there, the x values, and you get an F inverse out of it. Not for the full domain, but just for the part. Okay. So that's a quick little test on whether it has an inverse or not. All right, but the other part to this is then, well, all right, so it has an inverse, what is it? And like I said, you know, we had the first one, we had 2x, x divided by 2, that makes sense. Inverse function does the opposite. 2 times x divided by 2, the inverse. Well, sometimes it gets a little more complicated, but that's basically the idea. But let's find some inverse functions. And the first one to start with is, let's just start with the table, because this gets us used to the idea of what we're going to do here. We've already looked at it. So say we've got this table, and it's 1 to 1. X is 1, 2, 3, and 4. All right. And then f of x is 6, 10, 15, and 25. So what they want us to do on this, find the inverse function. Well, find the table. We're not going to actually find the function, what the function is, the expression. Let's find the table. That would be the table for my f inverse. The f inverse table here that goes along with this. All right, so we talked about it just earlier when we did the 2x and the x over 2 thing. What do we see on the table for the function and its inverse? What happened to the tables? Flipped. They flipped. That's all you have to do here is flip the table. In other words, here got x and y, so here, flip those. One of the x's over here will be the y's over here, and one of the y's over here will be the x's here. So you just flip the table. Make your x's the y's and the y's the x's. So here, these are the x's, well, they'll be the y's down here. That's all you have to do. These are the y's, so those will be the x's up here. That's all you have to do. That's what an inverse does. Okay? Flip the x's and the y's. Pretty simple, huh? Just have to know that's what you got to do. Okay. All right. Now, what if we have an equation. So number 2. Yeah, so just first of all point out, that's a line, slope 5, y-intercept 7. That's going to be 1 to 1. That's going to have an inverse, right? So what is the inverse? Well, the trick on that is really pretty much the same thing we just did. What do we do here? We switch the x and the y's. Well, for the inverse function, you do the same thing. Switch the x's and the y's. So this is, and maybe first of all, write instead of f of x, write y. Because what we're going to do is to find the inverse, switch the x's and the y's. Isn't that what the inverse does? Switches the x's and the y's. Now, the inverse function is in there, but guess what? To get the inverse function, we need it in y equals. So solve that for y. Solve that for y. So when you flip them, yeah, your y is no longer going to be solved for in most cases. So that's the second step on that. Flip the x's and the y's. That's our first step. Well, his first step was change that to y, but the next step after that, switch the x and the y, and then the third step, solve for y. So what? Subtract 7, divide by 5. So that's x minus 7 over 5 equals y. Now right there's your inverse function. F inverse, f to the negative 1 power it looks like, but that's f inverse, is this right here. Yes? Not too bad. The trick is sometimes it's a little more complicated. So a couple more just to point that out. All right. Number 3. What about f of x equals x minus 1 over x plus 3? Haven't seen those in a while, but x minus 1 over x plus 3. Again, what we're doing is finding the f inverse. All right, so that's y equals x minus 1 over x plus 3. To find the inverse, switch the x's and the y's. Make the switch. X equals, now in this case we've got 2 x's, so it'll be y minus 1 over y plus 3. And in essence, that's the inverse. However, it's not quite in the form we need. I need to solve it for y. What would I do?
Can you multiply both sides by y plus 3?
Multiply both sides by y plus 3. I'm with you there. Because, cancel out. Y plus 3 there. Now over here, of course that doesn't cancel out, so you have to go ahead and multiply the x times those. xy plus 3x would be that. Equals y minus 1. Now what? Unfortunately, we can't just add 1 here. Why? There's another y term. So you need those y terms together on one side, and then the non-y terms, say it that way, on the other side. You know what I'm saying? So I need these y terms together on one side. And so it doesn't matter. I'm going to subtract the y to this side. kind of go with that. This one doesn't have a y, so we'll put it to the other side, so subtract 3x. And so that'll get rid of that and that. So what do I have? xy minus y on this side equals minus 3x minus 1, or vice versa. Yes? Okay. Out of room there, so let me write it back here. xy minus y equals minus 3x minus 1. Well, trying to solve for y, I need to combine these, but can't really. Just factor off the y. Factor off the y here, that'll make it x minus 1 in parentheses there. Then all you have to do is divide off the x minus 1. Y equals minus 3x minus 1 over x minus 1. Hey, that's your f inverse function right there. So that one was a little harder to, that probably wouldn't be what we would have guessed. This was our original function, that's the f inverse. Yeah. I wouldn't have guessed that, but that's what it is. Okay, question? Show you one more of those. There's a point to be had about that. Number 4. F of x equals square root of x minus 9. Again, what I want to do is find the f inverse. All right, so that's y equals square root of x minus 9. So the inverse function will be the switch of those two. Switch the x's and the y's. Now I need to solve for y. So we haven't solved a whole lot of square root equations, but how do I solve? So my y's under the square root, so I need to get rid of the square root. How do I do that? Square both sides, yeah. So here I'm going to square both sides. So that side's x squared. The square and the square root cancel out. There you go. This one, really a lot easier than this previous one. All I have to do then, add the 9. And so my inverse is that. F inverse of x is x squared plus 2. And that one probably does make more sense. You got the square root, so you got the x squared, then you got the minus 9, the plus 9. So yeah, it's doing the opposite, but this is the process to go through to confirm that. Okay? Now, one point here. You notice something about this? Because we didn't mention it, but f, the function, has to be what? 1-to-1? Pass the horizontal line test. So does the f inverse. It passes the horizontal line test. Huh? We got a problem, don't we? Well, the deal is here, and I haven't talked about it, but so let's think about it. So here it is. That's shifted 9 over. All right. So it passes the horizontal line test. What's my domain and range? I mentioned range before today, but what's the domain and range there? What's the domain? The x values. 9 to infinity. What's the range? The y values. 0 to infinity. Okay. Guess what? That's my f. Guess what my domain and range for f inverse is going to be? They're going to switch. The x's and the y's switch, so do the domains and ranges. So the range over here is the domain over here. The domain here is the range over here. Everything switches. So what's the deal on this? I'm not talking about the whole function because I'm only wanting domain 0 to infinity. i.e. x greater than 0. So there is a restriction here on this. It's not the whole function, it's just x greater than 0. Greater than or equal to. All right. Make sense? A little bit?